behind the 3 hydrogen atoms attached to the carbon atom in the front, giving the arrangement a neatly distributed look. And so the arrangement is known as staggered conformation. All the arrangements between the eclipsed and staggered positions are known as skew conformations. In the eclipsed conformation, the molecule is the least stable as the repulsive force between the electrons is the maximum. This is due to close spatial arrangement of the carbon-hydrogen bonds. In the staggered conformation, the molecule is the most stable, as there is minimum repulsive force between the electrons. This is because the carbon-hydrogen electrons are the farthest from each other. The repulsive interaction between the electron clouds in a molecule, which affects the stability of a conformation, is called torsional strain. Its magnitude depends upon the angle of rotation about the carbon-to-carbon bond. This angle is known as torsional or dihedral angle. The energy difference between eclipsed and staggered conformations is 12.5 kilojoules per mole, which is easily overcome at room temperature and pressure. Due to this, it is not possible to separate different conformation isomers of ethane. Now that we have seen what conformation means, let's learn the 2 standard visual representations used to explain it. These are known as sawhorse projection and Newman projection. In sawhorse projection, the molecules are viewed along their molecular axis, that is, at an oblique angle. Here, the carbon-to-carbon bond is shown as a long straight line, whose upper end is bent slightly either towards the left or towards the right-hand side. The front carbon is shown at the lower end of the line, and the back carbon at the upper end. Each carbon has 3 hydrogen atoms attached to it. These bonds are shown with the help of 3 lines attached to the carbon atom. These are inclined at an angle of 120 degrees to each other. Using sawhorse projection, the 3-dimensional structure of the eclipsed and staggered conformations can be easily visualized. In Newman projection, the carbon-to-carbon bond conformation is viewed head-on, that is, front to back. The carbon atom at the front is represented as a dot, and the carbon atom at the back is represented as a circle. The hydrogen atoms attached to the carbon atoms are shown by lines. The bond angle between these lines is kept at 120 degrees. The hydrogen atoms connected to the carbon atom in the front are represented by longer lines, and those connected to the carbon atom at the back are represented by shorter lines. Using Newman projection, an unsaturated hydrocarbon with a double bond in between the carbon atoms is called an alkene. Alkenes are also called olefins, which means oil forming, as its first member, ethene, on reacting with chlorine, forms an oily substance. As you have studied, a carbon-to-carbon double bond consists of 1 strong sigma bond and 1 weak pi bond. A sigma bond is formed due to the head-on overlap between 2 sp2 hybrid orbitals of two carbon atoms, whereas a pi bond is formed due to the sideways overlap between two pure 2p orbitals of two carbon atoms. Due to the presence of a double bond, an alkene has two hydrogen atoms less than corresponding alkane. Hence, the general molecular formulae of alkanes is CnH2n. The pi bond, which consists of loosely held delocalized pi electrons, serve as a source of electrons for the electron-seeking reagents. Thus, the electron-seeking or electron-deficient reagents, called electrophilic reagents, attack weaker pi bond in alkenes and form corresponding saturated compounds. The presence of the weaker pi bond makes alkenes more reactive than the corresponding alkanes. The IUPAC name of the alkenes can be divided into two parts, that is, root word, which indicates the length of the carbon chain, and suffix -ene, which indicates the double bond. For example, the IUPAC name of an alkene with two carbon atoms can be divided into two parts, that is, root word eth plus the suffix -ene. Hence, the IUPAC name is ethene. In the IUPAC system, alkenes are named by replacing the suffix -ane of the corresponding alkanes by the suffix -ene. For example, ethane is named from ethane by replacing the suffix -ane with -ene. For alkanes with more than 3 carbon atoms, the carbon with a double bond is given the least number, and the number is indicated in the name. For example, but1-ene, but2-ene. An alkane with an alkyl group as a substituent is numbered in such a way that carbon with double bond gets least number. While naming, the number of the carbon atom with the substituent and the name of the substituent, that is alkyl group, is written as a prefix to the name of the parent carbon chain. For example, the following molecules are named as 2-methyl-prop-1-ene, 3-methyl-but-1-ene respectively. In higher alkenes, molecules can be arranged in more than one way. For example, the molecule of alkene with 4 carbon atoms, that is C4H8, can either be arranged as but1-ene, but2-ene, or 2-methyl-prop-1-ene. These are called structural isomers. In addition to this, it is observed that C4H8 shows 2 distinct special arrangements. They are cis-2-butene and trans-2-butene. These are called stereoisomers. Thus, higher alkenes are said to show both structural and stereoisomerism. In structural isomerism, they show chain and position isomerism. In stereoisomerism, they show geometrical or cis-trans isomerism. In a molecule of C4H8, all the carbon atoms are present in the form of straight or branched chains. For example, structures 1 and 2 have straight chains, whereas structure 3 has a branched chain. Structures 1 and 3 and 2 and 3 are said to be chain isomers of each other. When in two structures, the position of the double bond alone is different, They are said to be position isomers. Structures 1 and 2 are position isomers. A compound like but2-ene shows two distinct configurations or spatial arrangements, and hence, its molecules are said to show geometrical isomerism, a type of stereoisomerism. When the two CH3 groups attached to each carbon atom of the double bond are on the same side, the isomer is called a cis isomer. On the other hand, when the two CH3 groups attached to each carbon atom of the double bond are on the opposite side, the isomer is called as trans isomer. Due to the difference in the spatial arrangement, cis and trans isomers have different melting points, boiling points, dipole movement, solubility, and many other properties. For example, the cis but2-ene molecule is polar, whereas the trans but2-ene molecule is non-polar. This is because in a cis but2-ene molecule, as the two CH3 groups are on the same side of the double bond, there is a greater, hence the molecule is polar, CH3 bond dipole on each side, causing distinct positive and negative regions in the molecule. However, in case of a trans but2-ene molecule, the two CH3 groups are present on the opposite sides of the double bond. Thus, the bond dipoles of each CH3 bond cancel each other, making the molecule non-polar. Hence, we can conclude that trans isomers are more stable than cis isomers. Alkenes can be prepared from alkynes, alkyl halides, vicinal dihalides, and alcohols. Let's look at each of them in detail. To obtain alkenes from alkynes, we carry out partial catalytic hydrogenation. During this reaction, addition of a hydrogen molecule, that is, addition of two hydrogen atoms, takes place across the triple bond of the alkyne. There are two catalysts that are commonly used. One is palladized charcoal, which is partially deactivated using compounds like barium sulfate or quinoline. It is also known as Lindlar's catalyst. The other catalyst is sodium in liquid ammonia. For example, ethine, on reduction with palladized charcoal or sodium in liquid ammonia, forms ethane. Similarly, propine, on reduction with palladized charcoal or sodium in liquid ammonia, forms propane. Depending upon the nature of the catalyst used, a higher alkyne can be reduced to cis or trans alkene. Lower alkynes, such as ethine and propine, and higher terminal alkynes do not yield cis-trans isomers upon hydrogenation. When the catalyst used is Lindlar's catalyst, the alkene obtained shows cis geometry. When the catalyst used is sodium in liquid ammonia, the alkene obtained shows trans geometry. For example, 2-butene, on reduction with palladized charcoal in presence of quinoline, forms cis-2-butene. However, 2-butene, on reduction with sodium in the presence of liquid ammonia, forms trans-2-butene. Alkenes can also be obtained from dehydrohalogenation of alkyl halides. When an alkyl halide is heated in presence of alcoholic potash, it gives an alkene and one molecule of halogen acid is eliminated in the reaction. The hydrogen atom for the halogen acid is obtained from the carbon atom adjacent to the carbon atom attached to the halogen atom. The carbon atom attached directly to halogen is called alpha carbon, whereas the adjacent carbon is called beta carbon. Hence, the reaction is known as beta elimination reaction. As hydrogen and halogen atoms are removed in the form of halogen acid from alkyl halide, the reaction is also known as dehydrohalogenation reaction. For example, 1-chloroethane on heating with alcoholic potassium hydroxide forms ethene. During this reaction, the hydrogen and halogen atoms on adjacent carbon atoms of 1-chloroethane are eliminated in the form of hydrochloric acid. In a dehydrohalogenation reaction, if there are two possible positions where the double bond can be formed, then the product obtained is governed by Saint-Zeff's rule. Saint-Zeff's rule states that elimination will predominantly proceed to the formation of olefin in which the double bond is highly substituted. In other words, the hydrogen atom will be removed from the carbon atom possessing lesser number of hydrogens. The rate of reaction depends on the nature of alkyl group and the halogen respectively. The rate increases from primary to tertiary alkyl halides as shown here. The rate is also affected by the halogen atom attached and is the highest for iodine and lowest for chlorine. Another way to obtain alkenes is by the dehalogenation of vicinal dihalides. In vicinal dihalides, the two halogen atoms are attached to two adjacent carbon atoms. When such dihalides are treated with zinc metal, the zinc atom removes the two halogen atoms, forming zinc halide, leaving behind an alkene in the process. This reaction is also called dehalogenation, as zinc removes two halogen atoms simultaneously. For example, when dibromoethane is treated with zinc, it forms ethene and zinc bromide. And when 1,2-dibromopropane is treated with zinc, it forms propene and zinc bromide. Alkenes can also be obtained from alcohol using acidic dehydration process. When heated with concentrated sulfuric acid, the OH group of the alcohol and one hydrogen atom from the adjacent carbon atom are eliminated in the form of a water molecule, forming an alkene. Hence, the reaction is said to be acidic dehydration of alcohol. An example of this would be the dehydration reaction of ethanol on heating with concentrated sulfuric acid to form ethene. During this reaction, the hydrogen atom and the hydroxyl group from adjacent carbon atom are eliminated in the form of water to form ethene. Dehydration takes place in three stages. First, the alcohol is protonated by the acid catalyst to form a protonated alcohol. Secondly, the protonated alcohol loses a water molecule to give a carbocation. Finally, the carbocation formed loses a hydrogen ion and forms a double bond. Satzev's rule also governs the dehydration of alcohols. For example, in the dehydration of 2-butanol, there are 2 possible positions for the double bond. However, 2-butene is more substituted than 1-butene. Hence, the more predominant product is 2-butene. Thus, we see that alkenes can be obtained by many different methods. Now let us look at the physical properties of alkenes. Alkenes are colorless hydrocarbons. Except for ethene, all the other alkenes are odorless as well. The first 3 members of alkene homologous series are gases, the 4th to 14th are liquids, and all members above 15th are solids. Being non-polar compounds, alkenes are insoluble in water, but soluble in non-polar solvents like benzene and petroleum ether. Alkenes are unsaturated hydrocarbons consisting of a sigma bond and a pi bond. The typical reactions of alkenes involve the breaking of the weak pi bond to form 2 sigma bonds. Such reactions are called addition reactions. These addition reactions are usually electrophilic in nature, as the pi electrons of carbon-carbon double bond are available to any species seeking electrons. Let us study the following reactions in alkenes. Addition of dihydrogen, addition of halogens, addition of halogen acid, addition of sulfuric acid, addition of water, oxidation, ozonolysis, polymerization. Let's start with addition of dihydrogen to alkene. Alkenes react with dihydrogen in the presence of catalysts like finely divided nickel, palladium, or platinum to form alkanes. Such addition reactions are always cis addition reactions. For example, ethene in the presence of finely divided nickel, palladium, or platinum yields ethane. Similarly, propene yields propane. Now let's look at the addition of halogen to an alkene. Alkenes react with halogens such as chlorine and bromine to form vicinal dihaloalkanes. However, they don't react with iodine under normal conditions. For the reactions with chlorine and bromine, the alkenes and the halogens are mixed together in an inert solvent like carbon tetrachloride. Ethene reacts with bromine to give 1,2-dibromoethane. This reaction proceeds via the formation of an intermediate called cyclic bromonium ion. During the addition reaction between ethene and bromine, the reddish-brown color of bromine gets decolorized due to the formation of dibromoethane. Hence, this reaction is used as a test for unsaturation. Let us now look at the addition of halogen acid. Alkenes react with halogen acids to form haloalkanes. In the reaction with alkenes, hydrogen iodide is more reactive than hydrogen bromide, which is more reactive than hydrogen chloride. In the case of symmetrical alkenes, only one product is formed. For example, ethene on reaction with hydrogen bromide gives bromoethane, or 2-butene with hydrogen bromide gives 2-bromobutane. However, in the case of unsymmetrical alkene, two products are formed. For example, propene reacts with hydrogen bromide to form 2-bromopropane and 1-bromopropane. Of these, 2-bromopropane is a major product. This is in accordance with Markovnikov's rule, which states that during the addition of an unsymmetrical reagent to an unsymmetrical alkene, the negative part of the addendum is added to that unsaturated carbon which possesses lesser number of hydrogen atoms. In the reaction between propene and hydrogen bromide provides the electrophile H+ that attacks the carbon-carbon double bond, leading to the formation of primary and secondary carbocations. The secondary carbocation, being more stable, is formed readily. This secondary carbocation is attacked by the bromide ion to form 2-bromopropane. Hence, 2-bromopropane is a major product. However, the addition of hydrogen bromide to unsymmetrical alkenes like propene in the presence of peroxide is on the contrary to Markovnikov's rule and is known as anti-Markovnikov's addition or peroxide effect or Kharash effect, as it was first observed by M.S. Kharash and F.R. Mayo in 1933 at the University of Chicago. The peroxide effect takes place via the free radical mechanism. In this reaction, initially benzoyl peroxide undergoes homolysis to form benzene free radical. This attacks hydrogen bromide and results in the generation of a bromine free radical. This bromine free radical further propagates the reaction by attacking the double bond in propene. Hence, propene undergoes homolytic cleavage to produce less stable primary and non-stable secondary free radicals as shown here. The secondary free radical attacks hydrogen bromide to form bromopropane, and the primary free radical attacks hydrogen bromide to form 2-bromopropane. Thus, 2-bromopropane is formed as the major product. Now let us move to the addition reactions of alkene with sulfuric acid and water respectively. Alkenes react with cold concentrated sulfuric acid in accordance with Markovnikov's rule to form alkyl hydrogen sulfates. For example, ethene and propene react with cold concentrated sulfuric acid and form ethyl hydrogen sulfate and propyl hydrogen sulfate respectively. Alkenes react with water in accordance with Markovnikov's rule. In the presence of concentrated acids like sulfuric acid, a water molecule adds to an alkene molecule across the double bond to form alcohol. For example, 2-methylpropene reacts with water in presence of concentrated sulfuric acid to form 2-methyl-propan-2-ol. Let us now look at the oxidation reactions of alkenes. Alkenes, on reacting with cold dilute aqueous solution of potassium permanganate, which is also called Bayer's reagent, produce vicinal glycols, that is, 1,2-diols. For example, ethene, on reaction with Bayer's reagent, forms ethane 1,2-diol or ethylene glycol. As the purple color of potassium permanganate decolorizes with the formation of glycol, this reaction is used as a test for unsaturation. Depending on the nature of alkene and experimental conditions, alkenes react with oxidizing agents such as acidic potassium permanganate or acidic potassium dichromate to form ketones or acids. For example, 2-methylpropene, on reacting with acidic potassium permanganate, gives propan-2,1 or acetone. On the other hand, but-2-ene, on reacting with acidic potassium permanganate, gives ethanoic acid. Let us now look at the addition of ozone to an alkene, which is also called ozonolysis. Alkenes react with ozone to form ozonides, which, on further hydrolysis, in the presence of zinc, form either aldehydes or ketones or both. For example, in this reaction, the ozone molecule is added across the double bond in ethene to give ethene ozonide. This, on hydrolysis, forms formaldehyde or methanol. The oxidation of alkenes by ozone to form ozonides, followed by its decomposition with water, is termed as ozonolysis. This reaction is useful in locating the position of the double bond in an unsaturated molecule. Let us look at another example of ozonolysis reaction of propene. Here, first propene and ozone react to form propene ozonide. The propene ozonide, on further hydrolysis, in the presence of zinc, undergoes cleavage to form ethanol and methanol. The products formed helps us to determine the position of the double bond in propene as shown here. Let us move on to the last reaction, that is polymerization. Alkenes undergo addition polymerization reaction when heated under pressure in the presence of suitable catalysts. In this, a large number of molecules of the same species join together to form a giant molecule called a polymer. The simple compound which forms the polymers are called monomers. For example, ethene, when heated to 1000 degrees Celsius under 1000 atmospheric pressure, undergoes polymerization to form polythene. Aromatic hydrocarbons containing 2 or more fused rings are called polycyclic aromatic compounds or polynuclear aromatic hydrocarbons. Coal tar is the main source of polynuclear aromatic hydrocarbons. These hydrocarbons possesses either a linear or an angular structure. An example of a hydrocarbon with a linear structure is naphthalene or anthracene, and that of with an angular structure is phenanthrene and pyrene. These hydrocarbons are carcinogenic. That is, they cause cancer. Examples of polynuclear hydrocarbons that cause cancer are 1,2-benzanthracene, 3-methylchloranthrene, 1,2-benzpyrene, 9,10-dimethyl 1,2-benzanthracene, and 1,2,5,6-dibenzanthracene. There is no general method by which we can predict as to which polynuclear hydrocarbons will be carcinogenic. However, it is found that the number and position of certain groups such as methyl, hydroxide, cyanide, and methoxy in these compounds give rise to carcinogenic tendencies. These polynuclear aromatic hydrocarbons enter the environment due to the incomplete combustion of coal, petroleum, tobacco, etc. On entering the human body, these compounds undergo various biochemical reactions and damage DNA. This causes a sudden change in the DNA structure, leading to cancer. The elimination of carcinogens from the environment can reduce the incidence of cancer to a great extent.